to the DE 24/7 podcast. My guest today is COMSOL's Vice President of Sales, Phil Kinnane, and he's here with us today to discuss simulation-led design. Welcome to the podcast, Phil.
Thank you very much, Brian. It's great to be here.
Great. Well, as I said, we're going to be talking about simulation-led design, and we've seen an increased focus in the industry on promoting this idea. From your perspective, how successful do you think these efforts have been?
Yeah, I think those efforts have been very successful, and I think you can see that if you look at sort of the statistics of the computer-aided engineering or CAE market. You can see that there's been an increase percentage-wise, usually in the double figures for all of the software that is bound within the CAE market. And that the increase in or the growth, if you like, of the usage and of the industry itself is far outpaces sort of other indicators such as inflation or productivity rates. So it's fairly obvious that simulation-led design is becoming more and more integral to a large number of organizations and companies. And the reasons why, I think, would be because the computers, of course, are getting a lot better. They can handle far greater and bigger and more complicated models. They can also do so in a much faster pace. So if you take a step back, if you can model something that's a lot larger, and if you can model it quicker, then of course the answers, the data, whatever it is, the use from that model that goes to other parts of the company are going to be of much greater quality. Therefore, you're going to make use of that. But for us as a company where we and a software where we have concentrated on being able to model phenomena where many different types of physics are coupled to each other, multi-physics applications, the ability to be able to look at different physics and how they react to each other and affect each other has been increased because of the ability to be able to do far more computations now than you used to be able to do before. So back in the day when engineers or simulation engineers had to just concentrate on a specific physics, the most important one, maybe it's structural mechanics, maybe it's fluid dynamics, they would also have to more or less ignore or assume some values for other participating physics in their application so that they could actually get an answer for the physics which is of most importance to them. Now they don't need to do that anymore. Now they can consider all of the physics that affect a certain phenomenon. And that means, of course, that you get a much more accurate solution. That means you can say with a greater fidelity how a certain component is going to react or how a certain process can be controlled in a much more efficient way. And so it's fairly obvious that if you can do that, then you can start saving on costs, optimizing your devices, optimizing the amount of material, optimizing the amount of energy that needs to be put into a process, and which all, of course, leads to saving money.
Do you think that there's more work that needs to be done than to make simulation more accessible so that more people can take advantage of these benefits?
So I've been involved in this industry, the CAE industry, and with COMSOL Multiphysics now for 20 years. And so I've seen it go through the period where the computers and hardware and so forth that are able to or that are used to do simulation have gone from rather rudimentary or quite slow and clunky, if you like, to now where everyone's accessing the cloud. You can do parallel processing. The size of a model that you can say solve in a reasonable time now is orders of magnitude greater than what you could do 20 years ago. Not only has it been because of the increase of the ability of hardware, but also because algorithms and our programming abilities have also increased. So research has been done during the last 20 years looking at solvers, looking at different ways in which you can set up the numerical methods that can allow a much larger model to be solved or to be solved in a far quicker rate. And I think that these things will continue to occur, but if we take hardware, for example, I don't see any sort of huge shifts, if you like, than maybe what I saw 10 years ago when single processors went over to multiple processors and where parallel processing was occurring. Maybe they're on the horizon. Maybe something like quantum chips or something like that will kick it along or take it up, get past a certain threshold so that we're looking at even more computational power that can contribute to simulations. But if we are to sort of take a step back from the technology, we've done a really good job with the technology. Now maybe it's time to look at the use of that technology. And it's a situation where why should a company, why should an organization be reliant on a few experts that are great at simulation, that are great at the physics, that are great at the numerical methods, but there's only a few of them, and a large number of the engineers that are reliant on the data that comes from simulations. Maybe they're working in the design department, maybe they're working with the manufacturer of a product or a component, maybe they're running a process. They're not exactly conversant in all of the different aspects of simulation, but they're still very smart people. They still know what it is that they're working with. Some of them have been working with it for 10, 20, 25 years, and they have a lot of experience which they can contribute to the overall sort of optimization or development of that component or process and the like. So why not give them simulation? Like if you, just to get sort of rather philosophical about the whole thing, books and reading and literature was once the purvey of a few people throughout the world that, basically you had to write out a book and copy a book and then give it to someone else, and then that person could read it. But the masses were all illiterate, and they didn't have the ability to make use of the power of books and literature and the like until the printing press came along. And when the printing press came along, bang, suddenly everyone had the reason, had the initiative, and then had the ability to be able to read. And if you could do that, then they could read so many more copies of the same book, and everyone can partake in that knowledge and so forth that that book gave them. In the same way, why can't models be like that? Why should they be the purvey of the one or the person that is the expert? Why not give the ability to do simulation, the ability to understand the data, the ability for you as the person who requires that data to input new figures, new conditions, new operating parameters that affect the process that you're working with, and you optimize it rather than having someone sitting in another building or some expert whose time is very valuable doing it for you.
As we move into 2021, do you see any new trends or factors in the industry that are going to increase the use of simulation and encourage that kind of democratization that you're describing?
Yes, certainly. From thinking about how to build simulations in a completely different way than what we've done so far. And so far, we consider the model of a certain component or process as a whole. And so that everything that's involved in that model has to be accessible, available, can be changed. And that requires you to have the knowledge about everything that goes into a model that can be changed, just to make sure that they are all are working symbiotically with each other. But if you, as say the expert, could put together some type of piece of software that takes away a lot of that complexity and instead gives me, as say the operator or the design engineer, a piece of software that's actually quite easy to use, very intuitive. It only has a user interface where all of the different input menus and windows and so forth are parameters that I understand, that I know how they should be reacting according to other inputs that I put in there. Then that, I believe, is the way in which, and I'm seeing it, we're doing it ourselves, of course. We call them simulation apps. But that is how I see it spreading from just the few to the many.
Circling back a little bit on hardware, are you seeing in the market, an increased use of high performance computing resources in a simulation environment that can, help sort of enable a lot of this?
Yeah, well, HPC, of course, has been integral to solving bigger models faster. There is also, and which I've already sort of addressed, I believe, in earlier answers, and so that, of course, is important. But the important part of that fact is actually the ability to do parallel processing, the ability to write the algorithms and the methods and so forth that can either split up a rather complicated and large model so that it can be solved in parallel on many processes. But HPC also gives a far greater and easier way for networking. And so offices or units or different organizations can all communicate with each other a lot more effectively. And when I say communicate, I'm not necessarily talking about email or anything like that. I'm talking about passing data from one source to another source. And through there, then it allows you to be able to partake of uh, innovation and models and simulations and the like that someone else in your organization has done, but has done in another completely different part of the world. So I see HPC as being a fantastic way in which, if there is some standardized way of building simulation apps or models for that matter, but basically simulation apps that are really easy to use, then if you have a bunch of similar engineers, let's say they're operators of a certain process and these processes are being run throughout the world, but the same engineers, the same types of engineers that are running these processes can all access the same type of simulation app, then they can start communicating through um, the inputs and the outputs and the data and so forth that these simulation apps provide them with their colleagues and so forth that are working on similar processes. So I see HPC as being able to solve much, much bigger models, much faster, but also by being able to collaborate between different units within your organization.
That's a good segue because I know there's a new release of COMSOL multiphysics. How are some of these trends being reflected in the COMSOL platform? I know that app approach has been a key piece. What else are we seeing?
And so the app approach, as you mentioned, is always it's sort of the biggest thing that we've been working with, and it's starting to take hold within the market. Now we're finding the customers that aren't coming to us because of the reasons of that we can model something, that they can necessarily build a complicated model. It is, of course, always the fundamental to a simulation has to be the model, but people are starting to come to us for the main business reason of being able to use the apps, being able to get a much larger number of people within their organization participating in simulation, communicating with each other, communicating back to the expert who built the model in the first place, and that's why they are quite happy to use COMSOL, or maybe even move from some other software to COMSOL because of these reasons. But there are other things that are also involved. The general development of our software continues apace. We improve solvers and meshing algorithms, not by just a few percentage, but usually from release to release, we can increase their speeds by 30, 50% sometimes. And then we also branch out into different types of multiphysics applications, ones that have always been way too difficult to model once upon a time, where you just basically tried to assume behavior that's coming from certain physical phenomena and concentrate on a single physical phenomena. So we have a new product, for example, the polymer flow module. Now, polymer flow has been out there for quite a long time, and there's software that has been able to model it in your casting and so forth of polymerization processes and components that come from polymers. It's been a lot harder to have these types of material properties that are the polymer be explained in far greater detail or with far greater accuracy because of the contributing other physics that are involved. So temperature is a physics that's usually very important in polymerization processes, but also stress, structural stress, sometimes chemical reactions. And so all of these types of things can now be included rather easily, can be used by basically anyone who works within that within that industry because of our ability now to be able to solve more and more complicated types of applications.
All right. Well, thank you very much for joining us today, Phil. And we'll see you next time on the DE 24/7 podcast.